All right, there we go. So, Chemistry 3101, we're in Chapter 7. And keep in mind, we're skipping Section 7.5, which deals with biological alkylation. I will not be asking you anything about biological alkylation on your quiz. Okay, so Section 6.7 deals with E2 reactions. Now, if you remember, last lecture, we discussed SN2 reactions. So an SN2 reaction, S stood for substitution, N stood for nucleophilic, and 2 stood for bimolecular. And an E2 reaction is similar in that E stands for elimination and the 2 stands for a bimolecular. And if you remember way at the beginning of this chapter, I talked about the difference between a substitution and elimination reaction. So now we're just going to get into elimination reactions in more detail. So if we take an alkyl halide, in last class we talked about alkyl halides in depth. We talked about a primary, secondary, tertiary alkyl halide. We discussed their nomenclature. Well, if you take an alkyl halide and you treat it with a strong base, maybe something like sodium hydroxide, right? That's a strong base. It's conjugate acid. Water is a weak acid. It can undergo a beta elimination, which we sometimes call the 1,2 elimination. Our book uses both. Sometimes he calls it beta elimination. Sometimes he calls it 1,2. And we end up forming an alkene. And we could draw a set of curved arrows for this, right? Our base is going to abstract the proton from this beta carbon. And we're going to form a double bond like this. And we're going to lose a leaving group. So we're abstracting a proton, generating this double bond here, and then we're also losing a leaving group all at the same time. And this is a concerted mechanism, right? We're having the proton transfer, right? Our proton transfer and our loss of leaving group are happening simultaneously. Excuse me. And so this is a concerted mechanism. Everything is happening together. An E2 reaction, E together is maybe the way you could think about it. And what are we generating? We're generating a functional group, right? We're making an alkene. So that's kind of interesting. Well, if we think about the kinetics of an E2 reaction, since it's a concerted mechanism where we do the proton transfer and loss of leaving group at the same time, this concerted elimination is bimolecular. It follows second order kinetics, right? Going right back to general chemistry 2, we say that the rate is equal to the rate constant times the concentration of the substrate, the alkyl halide, multiplied by the concentration of the base, okay? And so here's the E2 mechanism. I drew it on the last slide. You need to be aware of this mechanism. You need to be able to draw this mechanism. You need to be able to determine what the products would be once this mechanism occurs on a substrate. All right, so things you want to keep in mind are that if you have a leaving group, let's say an iodide, a bromide, or a chloride, the hydrogen that's going to be abstracted is on the beta carbon. So this is our alpha carbon here, the one that has the halogen or leaving group attached to it. This is the beta carbon, and that's why we call it beta elimination, right? Because we're eliminating a hydrogen on the beta carbon. Sometimes we call this dehydrohalogenation because we're losing a hydrogen and a halogen both at the same time for this molecule, right? We're losing a hydrogen and a halogen. So dehydrohalogenation is a term that will come up from time to time in this class. Now, what about the effect of that substrate, right? If you're thinking, well, hold on, Mr. Dion, I thought that sodium hydroxide, I thought you said that that could be a nucleophile. Didn't you tell me last class that sodium hydroxide could be a strong nucleophile? I did. Absolutely, I did. But whether sodium hydroxide functions as a nucleophile or a base, okay, is going to depend on the situation. Remember that when we had a primary or a methyl alkyl halide, that yes, hydroxide can do an SN2, a substitution reaction then, so the hydroxide behaves as a nucleophile. But what if I have a tertiary alkyl halide? And that's what's being represented here. You see that this is tertiary, right? We have all of these alkyl groups. We have 3 methyl groups here. Well, that is too sterically hindered for the hydroxide to act as a nucleophile, right? There's just too much steric hindrance here. There's too many groups blocking the way. And so if we just isolate one of those methyl groups and we draw one of the hydrogens, yes, I'm fully aware that there are 1, 2, 3 hydrogens, but this is for demonstration purposes only. If we just draw one of those hydrogens, you can see how that hydrogen can be abstracted even though the substrate is tertiary. Why? because this hydrogen is kind of on the periphery. It's not sterically hindered. So it's kind of like picking the low-hanging fruit, right? It's easy for the base to grab that proton. So the conclusion or the take-home message is that when the substrate is sterically hindered, when it's tertiary, E2 elimination is going to occur. Okay? All right. And we're going to see more examples of this looking forward. But if we're going to start making alkenes, right, we're starting to make alkenes, we need to talk about how to name an alkene, right? Because it's a lot easier for us to discuss alkenes when we're able to name them properly. Just like any other nomenclature that you've seen in this class, and you've seen the alkane nomenclature, cycloalkane nomenclature, alkyl halide nomenclature, if you understood the rules for the nomenclature of those types of compounds, you're going to find alkene nomenclature not all that bad, okay? So how do we name an alkene? Same way we name an alkane, but with minor modifications. The first thing is that we find the parent chain, and if you remember with alkanes, we just had to find the longest chain, right? That's all it was. Just find the longest chain and you're done. Well, with an alkene, it's a little different. You find the longest chain that includes the carbon-carbon double bond. So it's got to have that carbon-carbon double bond in it. You identify and name the substituents: methyl, ethyl, propyl, isopropyl, butyl, so on and so forth, chloro, bromo, iodo, etc. Then you assign a locant and a prefix to each substituent. Then you have to provide a locant or a number for the double bond as well. Now, a double bond is going to go through 2 carbons, right? A double bond needs 2 carbons. And so let's say your double bond, for example, let's say it went through carbons 2 and 3. You would identify it as carbon 2 was the number that you would give to the double bond. That's just an example. You list the substituents numbered in alphabetical order. You ignore prefixes except iso, cyclo, and neo, okay? When ordering alphabetically, the carbon-carbon double bond locant is placed either just before the parent name or just before the -ene suffix. And these are just some nuances about nomenclature. And bullet point number 5 is kind of hard to understand until you see an example of it. So an example would be, let's say you had this compound. So if I have this compound 5 carbons, that's pentane. If I put a double bond here and I number the longest chain, so to give the double bond is going to be at carbon 2, right? It's at carbon 2. So I could either call this 2-pentene, right? And that's what it means when it says just before the parent name. Or if you want to do it just before the -ene suffix, the way you do that is that it would look like this. It would say you'd put pent-2-ene, right? Pent-2-ene is just before the suffix, okay? So again, either one works. I'll just be honest with you. Most of my students use this, 95% of the time. Okay, so here we go. Here's some examples, right? Nomenclature is best learned by looking at examples. Here we have some examples of identifying that parent chain. Here we have pentane, and then we have pentene. Now, you're wondering, why isn't there a number associated with that? Well, they just left it out. So if we numbered it 1, 2, 3, 4, 5, this would actually be 1-pentene, or you could call it pent-1-ene. Either one is totally fine. If we look at the example of this alkane down here on the bottom left, you see that the longest carbon chain contains 8 carbons, and so it's an octane. But in this alkene over here, the longest carbon chain right here doesn't contain the double bond, and so the longest carbon chain has to contain the double bond. All right, that's rule number 1. Identify and name the substituents. My students are usually pretty solid at that at this point. You've got enough practice looking at different substituents. Assign a locant and prefix if necessary. Give the carbon-carbon double bond the lowest number possible. This is a really great rule, rule number 3. And the reason why is because with alkanes and alkyl halides, we had kind of a decision point here where if we had multiple substituents, we had to give the first substituent the lowest possible number. You don't even have to think about the substituents when you're dealing with an alkene. You just go with the carbon-carbon double bond, give it the lowest possible number, my friend, and you are done. Okay, that's all there is to it. So you can see that in this example here, they've given the double bond the lowest possible number. Here it doesn't have the lowest possible number, and that's it. Don't worry about the other substituents. You'll name those, and that's going to be just fine and dandy. Okay. There we go. So again, the locant for the double bond indicates where the double bond starts. And so this molecule here, this would be a 2-heptene. It would not be a 3-heptene, right? Because the double bond starts on carbon number 2. Just kind of a nuance there. You list the number of substituents in alphabetical order. Ignore the proper prefixes, so isoneo and cyclo. All right, and then again, I showed you this rule before, where since we have a 2-heptene, we can call it a 2-heptene, or we can call it a hep2ene. Either one is fine. You'll see that nomenclature rules are put forth by the IUPAC, the International Union of Pure and Applied Chemistry, and they tend to have changes from time to time or addendums that they add to it. So it's not enough to just give our molecule this name. We also have to designate whether the double bond is E or Z, and here it's E. And if you're wondering, hey, Mr. Dion, isn't that double bond also trans? Because I have a hydrogen here and I have a, couldn't I call it trans? 5,5,6 trimethyl hep2ene, wouldn't that be okay? Yeah, it would be. In this case, either one would actually be perfectly acceptable. All right, well, let's talk about the isomerism of alkenes. And we talked about how to assign E and Z designation for an alkene, and it's based off of the Kahn-Ingold-Prelog rules, where we just go off of atomic number, right? Fluorine has a higher atomic number than carbon, and so the fluorine has higher priority. Nitrogen definitely has a higher priority than hydrogen, and since these two groups are on the same side, it is Z, right? This is Z, which means zusammen. Zusammen, can I even spell that correctly? Took German for 2 years, but anyhow. So there we go. So that's a Z alkene. So you need to be on top of that. Again, if the top priority groups are on the same side, if they're cis to each other, then it's a Z isomer. If they're on opposite sides, if they're trans to each other, we call that E. So you need to be pretty on the spot with your Z and your E isomers for alkenes. Usually students are pretty good at that after having studied stereochemistry. My students are usually pretty good at the Kahn-Ingold-Prelog rules and assigning preference. Anyhow, let's move on from there and let's try a couple of problems. You can see I even threw one in here that isn't part of these problems, I don't think. But anyhow, let's take a look at the first one, C. What's the first thing we're going to do? We're going to identify the longest chain that possesses the double bond. I'm going to save us a little bit of time. So it's going to be this chain here. And you can see that there are 7 carbons in this chain. And hopefully it's abundantly clear that you would start numbering here, right? Because then you'd give the double bond the locant 2. So 1, 2, 3, 4, 5, 6, 7, like that. So this is some kind of 2-heptene. You could even write that down if you want. I like to do that sometimes, start making a laundry list of what I know. So it's not a 2-heptane, it's a 2-heptene. Your suffix is -ene because this is an alkene. Then we can identify the substituents, and we have a methyl group here, we have a methyl group here, and we have a methyl group here. So we have a methyls at carbons 2, 3, and 5. So it's a 2, 3, 5 trimethyl. We can add that on there. 2, 3, 5 trimethyl. There we go. 2-heptene. There we go. And I have a question for you guys while I'm putting this together into a big, beautiful nomenclature sandwich. Is this molecule cis or trans or E or Z? Could anybody help me with that? What would this molecule be? Cis or trans, E or Z? Could anybody give me a designation? Okay, I've got an answer. Yeah. Okay. I got an argument brewing here, right? Some people say it's E, some people say it's Z. Well, the answer is it's neither. Okay, it's this molecule is neither E nor Z, nor is it cis nor trans. Remember that there was a rule that I went over with you when we discussed cis and trans, that if you have a carbon in the double bond and 2 of the groups are identical, so I have a methyl group here and a methyl group here, then you cannot have cis trans or EZ isomerism. Okay, it doesn't exist, right? Because this methyl group is going to be on the same side as this, for example, but it's on the opposite side of this. And then you could think the same thing here. This methyl's on the same side here. It's on the opposite side. So just a quick rule. When you have a carbon in your double bond and two groups attached to it are the same. There's no E or Z. So I could save you a little bit of time on the next one. You see that this carbon has two hydrogens attached to it like this, so there's no E or Z with this molecule either. Now again, we identified the longest chain, so we have 1, 2, 3. I just did it like this. And if you're thinking, Mr. Dion, I went this way, okay, you're still going to end up with the exact same answer as somebody who goes like this, or it doesn't matter. I mean, oops, you can't do that. But if you did this, either way, you're going to end up with the same answer. All right, so there we go. There's the longest carbon chain. So it's got 1, 2, 3, 4, 5. If you don't follow me, we could number those 1, 2, 3, 4, 5 like that. So this is some kind of 1-pentene. We could put that down, 1-pentene, 1-pentene like that. And then what are our substituents? Well, we have 2 methyls, one at carbon 2 and one at carbon 4. And then we also have an isopropyl at carbon 3. So that means we've got a 3 isopropyl, right? I. We identify the letters being I, since we don't ignore the prefix iso. So we have iso, 3 isopropyl, 2,4 dimethyl, 1-pentene. So there we go. That's going to be the name of that molecule. All right. And again, E or Z, cis or trans, is irrelevant in this one. So let's move that one up there. I'm going to skip G for now and go over to this bicyclic one. Just to review, by naming a bicyclic compound, you could practice by naming this compound just by removing the double bond, let's say, because we tried naming compounds like that. But if you remember that when we named bicyclo compounds, that we went around from a bridgehead carbon, these are bridgehead carbons, and we numbered with the biggest bridge, right? We started with the biggest bridge, going to the smallest bridge. Well, this bridge has 2 carbons and this bridge has 2 carbons, but then we're going to invoke the rule that we want to give the alkene the lowest possible number. So that means we're going to start numbering either here or here. It doesn't matter, but this is going to be the bridge we're going to go to first. Right? We're going to go through the double bond bridge. So we have 1, 2, 3, 4, 5, 6, right? Because I go to the next bridge, that's the next biggest bridge, which is again 2 carbons, but this one's lower priority because it's not an alkene. So 5, 6, and then we go up here for 7. So this is some kind of bicyclo. Hopefully you remember how to do this. So it's a bicyclo. And then we have our square brackets like this. And then it's a bicyclo. We've got 6 carbons in the ring. So this is some kind of bicyclohex. Oops, sorry, hept. Sorry, we have a total of 7 carbons in the bicyclic structure. So bicyclo, hept 2-ene, and if you put bicyclo 2-heptene, that's fine. And then we put the number of carbons in each bridge. We have 2 carbons, 2 carbons, and 1 carbon. So we'll put those in. So we have 2, 2, 1, like that. And then we also have 2 substituents, don't we? We have a methyl group at carbon 2, and we have a methyl group at carbon 3. So that's going to be 2,3-dimethyl. So we can add that, 2,3-dimethyl. And there, that's going to be the name like that. Now, if you're intimidated by that one and say, whoa, that's a tough one. Well, again, the best thing to do is to practice nomenclature. You know, there's scientists that are actual experts in nomenclature. You know, these are people that practice nomenclature probably every day of their lives. Anyhow, just in the interest of time, I'm going to skip G. But of course, I posted a video the other day that shows you how to access the solutions manual if you are unaware of how to do that. So we have all the solutions. And again, these aren't just answers. Oftentimes, they have a guided solution that explains how to name the compound. Well, let's talk a little bit more about alkenes. And let's think about these 2 alkenes here. Right? Everybody that's hearing the sound of my voice, I'm pretty sure, could name these compounds pretty quickly. Trans-2-butene and cis-2-butene. If you look at these 2 molecules, it's probably not a huge surprise that the trans is going to be more stable than the cis, right? If you look at these, and if you look at these space filling models here, you know, it kind of becomes hopefully more abundantly clear that if you have the cis, when you look at the bond line structure here, it's not abundantly clear that these 2 methyl groups are crowding each other, that you have steric hindrance. But when you look at the space filling model, whoa, Nelly, you see that there's really some serious steric strain there. Now, if you're the kind of person that needs numbers to prove this kind of stuff, you're thinking, well, what's the heat of combustion of these alkenes, because we could compare the relative stabilities, and we did that in the alkanes chapter. It's something a little bit different, but if I compare the heats of combustion of these two compounds, which are both C4H8, right? They both have the same molecular formula, and you write out a balanced equation, if it's going to be identical, but if you look at the heats of combustion, they're different, aren't they? That's kind of interesting. Well, if you compare the values, you see that when you burn the trans, you release 2,682 kilojoules per mole, but when you burn the cis, you release more. That tells you that the trans was actually lower in energy, right? It was more stable because it released less energy, right? If it's really high, if it was a really unstable compound, like think of nitroglycerin, that's unstable. It's going to release a lot of energy, right? Well, that's why it's explosive. So the fact that this one released less energy tells you that it's more stable. It's more stable by 4 kilojoules per mole. Okay, so we can prove that numerically, again, by looking at the heat of combustion. If you're the kind of person who likes to see everything on a graph, so here we have the enthalpy plotted on the y-axis, and if you just look at the difference in the relative, energies here, you can see there's a difference of 4 kilojoules per mole, and that is simply, again, based off of the fact that these two methyl groups are going to sterically hinder one another, whereas here the two methyl groups are free. They're not sterically hindered. So you need to understand that the difference between trans and cis 2-butene, you need to understand that. And then you also need to understand the fact that when we have a stabilized, that when we have an alkene that is substituted with various alkyl groups, that the more substitution we have, the more stable the alkene becomes. So if you look at each one of these alkenes, they all have the same molecular formula, 1, 2, 3, 4, 5, 6. So they're all C6H12. Okay, every molecule here is C6H12. But if you compare the relative stabilities of these alkenes, you'll see that this molecule is going to be more stable than this, right? They're going to follow this pattern here, that as you add more and more alkyl groups to the double bond, it becomes more stable. And that's a rule that's going to come up over and over in organic chemistry. So it's one of those rules that by the time you're in organic chemistry 2 and you've been there for a few months, you'll forget probably that you saw this slide, but you'll know the rule. Okay, it comes up so often that the more substituted an alkene is, the more stable it is. Now, if you're the kind of person that's wondering, well, why would that be? Well, it's an electronic effect. Our book goes into very little detail about this, except to say it's an effect based on hyperconjugation. So basically, the orbital overlap between the alkyl group and the sp2 hybridized carbon, so it just stabilizes those carbons and therefore stabilizes the double bond. I'm not going to ask you about that. I'm not going to ask you about hyperconjugation. I'll just expect you to know this rule right here. The more alkyl groups we have on our double bond, the more stable it becomes. We spent a lot of time looking at cycloalkanes back in chapter 4, and you might be wondering, well, could I put a double bond in a ring? And the answer is absolutely we can. If you look at cycloalkenes, so here we have cyclopropene, cyclobutene, cyclopentene, cyclohexene, right? Ene, we use the suffix ene because they're alkenes. You might be wondering, well, why don't you call these cis or trans, cyclopropene? Why is it cis or trans cyclobutene? The reason why is because when you have less than 7 carbons in a ring, you can only have a cis alkene. It would be impossible to have a trans alkene. So that's why you leave that out. Now, if you have 8 carbons or more in your ring, you include that. You would include whether it's cis or trans. I'll be honest with you, we don't really look at a lot of examples where we have more than 8 carbons in a ring and have a double bond or anything like this. This is another rule that I usually don't ask my students about, which is Brett's rule. Do I even have it in here? No, I think I took it out. It basically states that when you have a bridged bicycloalkene, this should say alkene, not akene, an alkene, that you can't have a double bond. So let's say you have a molecule that looks like this. This is called norborane. You can have the double bond here, right? That can exist, okay? You can have the double bond here. That can exist, but you can't have a double bond at a bridgehead. So this can't exist, And then let me take this, if I copy and paste that. Anyhow, I'm going into too much detail about this, but it's Friday. I can't help it. There we go. And if I, come on, paste. So if you have all these norborine isomers, if you have the double bond here, that's okay. That's okay. But if you try to put the double bond at a bridgehead like this, or if you try to put it here, these don't exist. Okay, so you can't have a double bond touching a bridgehead carbon, right? These are the bridgehead carbons. So if you have a double bond touching those, it's not going to exist. And that's basically all our book goes into as far as details about that. Well, let me ask you a question, and I'm pretty sure you're all going to be able to nail this question pretty quickly based off of this point right here, that the more alkyl groups on our double bond, the more stable the alkene. So let's take a look at question 7.16. It just says, arrange the set of isomeric alkenes in order of stability. So isomeric just means all of these have the exact same molecular formula. Let's say we call these, 1, 2, and 3. Could anybody tell me which one of these would be the most stable? And it's not a trick question. Yeah, Josh is correct. Moira, Kayla, Lauren, you're all 100% correct, right? This is going to be the most stable. Which one's least? Which one would be least stable? Yep, 100%. You're all correct, right? This is going to be the least stable. And you're probably thinking, Mr. Dion, I hope the quiz is just this. Yeah. My students usually nail this. You're all 100%. Mackenzie, Jonathan, Courtney are all 100% correct, right? How did my students know that? If you're wondering, well, how did they know? The reason they knew is because this double bond here is tetra-substituted. So tetra-substituted. This bond here is di-substituted. And then this double bond here is tri-substituted. If you want to sound fancy to your friends, you hear me say alkene, or which means, double bond. An old-fashioned way of describing alkenes is to call them olefins. So an olefin or an olefins. So if I could just say this is an olefin and it's an alkene, and it's just one of those habits that die hard. I mean, once you work as an organic chemist or you spend any time doing organic chemistry, you'll hear people refer to alkenes as olefins all the time. So if you hear me say the word olefin, that just means you're dealing with a double bond. Oh yeah, here I go. So I have a slide here that just goes over Brett's rule really quickly. So here you have a bridgehead carbon, and since there's only 6 carbons in the ring, it can't exist. Since you have more carbons here, since you have 1, 2, 3, 4, 5, 6, 7, since you have 8 carbons in the ring here, it can exist. Again, if you build a model of these, it's pretty obvious why this can't exist. But basically, I'm not going to go into a whole lot of detail. I'll tell you right now, look, you can hear this from the horse's mouth. Okay, I'm not going to ask you anything about Brett's rule on your quiz, and we're not going to ask you about it on your exam. Okay, some things are just mountains or hills I'm not willing to die on. Well, let's get into stuff that is really important for an organic chemistry student. It wouldn't matter if you were in my class, Dr. Anderson's class, or any organic chemistry class in the world. This slide is important for you. Okay, so let's follow along. It says if you take a substrate right here, so we have this substrate, this alkyl halide. Here's our alpha carbon. We have a beta carbon here. We have a beta carbon here, and then we have a beta carbon here. Well, hopefully you notice that the 2 beta carbons that are in red are identical to one another. They're both just methyl groups. However, the beta carbon that I have highlighted in blue is different, isn't it? So remember that sodium methoxide can behave as a nucleophile, or it can behave as a base. So a nucleophile to do an SN2, that's what we've seen so far, or a base to do an E2. But since this is a tertiary alkyl halide, right, it's not going to do a substitution, is it? It's going to do an elimination reaction because this alpha carbon is too sterically hindered for the ethoxide to act as a nucleophile. All right. So what that means is that in the elimination process, it can pull off one of the protons. Let me fix this with my red pen. So it could pull off this proton in red at this beta carbon, which would give us this product over here, or it could pull off one of these protons here to give us this product here. And you see that they have two different names. The more substituted product, so this is more substituted alkene, we call that the Zaitsev product. And the less substituted product, so less substituted, we call that the Hofmann product. And you're going to hear me use those terms, Hofmann product and Zaitsev product. Now, again, the reason why the Zaitsev product is formed in a greater amount than the Hofmann product is simply because it's more stable, right? In this case, in this specific case, it's more stable than the Hofmann product, right? All right. So this E2 elimination, we say it's regioselective. Again, you have this region where you could pull off a beta proton, and you have this region where you could pull off a beta proton. If we want to draw the mechanism for the elimination of the proton in red, so if I draw the ethoxide anion like this, I could draw the curved arrow. So I'm going to do the proton transfer, generate the double bond, and lose the leaving group. If I redraw this guy like this, okay, so I also have these protons, right, these beta protons. I could do the same thing. I could draw the ethoxide again, and you need to be able to do this. I would show the proton transfer, formation, maybe I could fix that, the formation of the pi bond and loss of leaving group, right? That one is going to give you the Zaitsev product, and then this one, the one in red, is going to give you the Hofmann product. I kind of switched my colors from the last slide, didn't I? Anyhow. Now, if you're wondering, well, what if somebody was going to pay me all kinds of money to make this product? What if somebody said, hey, you know what, Kayla, if you could just make this for me, I will give you, $1,000 for every 10 milligrams you can make. Okay, well, they won't, not for this compound. But let's say it was a similar strategy. You could either make the Zaitsev product more substituted, or you could make the Hofmann product, and you're like, well, dang it. That means that every time I do this reaction on 100 grams, I'm going to end up with 29 grams of this and 71 grams. So I'm going to be throwing a lot of stuff in the trash. I don't like that. I don't want to throw stuff in the trash. I want to maximize the amount of money-making material that I can produce. How would I do that? Well, the answer is you can go to the cupboard, go to your reagent cupboard that you have in the lab, and you're going to carefully choose the correct base. Right? You can see that an organic chemist has to be a person that's really can think about multiple things at once. Okay, we say that organic chemists are kind of like acrobats to some extent. I don't know if you've ever seen in Johnny Carson, they'd get these people on there that could spin a plate with one hand, and then they'd play the accordion with the other one and sing a song. So you got to be able to kind of think and do more than one thing at a time. So let me answer this. How would you choose a correct base? It says here that there's data that shows that if you choose a bulky or sterically hindered base, it's going to favor the formation of that less stable Hofmann product, okay? And if you choose an unhindered base like ethoxide, it's going to favor the Zaitsev product or the more stable product. So this is a an unhindered base. So we'll call this an unhindered base, right? Hindrance, right? Think about it. If this is ethoxide, all you have is that little CH2 and CH3. But once you get into hindered bases, okay, so these are hindered, and this one is the most hindered. All right, just because all these alkyl groups over here are makes it kind of big and bulky. Well, let's think about it. If we're just thinking about it in terms of the Zaitsev product, let's think about it in terms of the Hofmann product. If you want to pull off this proton here. Well, the reason ethoxide is not going to pull off that proton, it's going to pull off this proton, is because the driving force is going to be to form the more stable alkene. So once you get to a bigger, bulkier base, it's going to be harder for it to grab this proton here, right? It's going to go for the low-hanging fruit because it's just too bulky to get in here, right? It's going to be like, oh, come to Papa. There we go. This one's a lot easier to grab, okay? And then once you get to something that's really bulky like this, it's like, no, I'm not going in there. That's way too, whereas this, it's going to be way more open to that one, okay? Give me a thumbs up if you follow me on that idea that I was just explaining. It's basically about how easy or difficult is it for it to grab this proton versus this proton? Right? That's all it's about. Which proton's easiest to grab? Well, with an unhindered base, it's going to be indiscriminate. It's just going to pull off the one that makes the most stable alkene. But once you get into hindered bases, it can't pull off this proton to make the more stable one, even though it wants to. Okay, it's going to have to go with this one because it's more open. That's all there is to it. That's it. That's all, as we say in French. Anyhow, there we go. So regioselectivity. I explained why a hindered base forms the Hofmann product, or the less substituted product. Other hindered bases that you might recognize, right? What was the one on the last slide? They had this one. So this would be 3-ethyl, 3-pentoxide, which we don't see an abundance of this one. Okay, but this one here, you're going to see a hell of a lot, which is potassium T-butoxide. In fact, my students get addicted to this base by the time they get to organic chemistry too. Every time I ask a question, they're like, potassium T-butoxide, Mr. Dion. And a lot of times they're right. Other ones that are popular are things like diisopropylamine. So diisopropylamine also has an acronym, which is DIPEA. So diisopropyl ethylamine, and then triethylamine is TEA. Anyhow, there's a holy host of them out there. There's another one, which is diisopropyl ethylamine, which is this one here, which is even named after a person. This is called Hunig's base. Hunig. All right, Hunig's base. I don't think that Hunig's base comes up in our book. But so if you're wondering, Mr. Dion, why do you bring up stuff that's not in our textbook? Just because Hunig's base is just super popular with organic chemists, even if it's not in our book. It might be in here. I can't remember. Anyhow, let's try some problems. Here we go. We're going to do just a good old E2 reaction. Imagine you're on the next quiz, and I say, hey, come on, show me what you'd get if you tried an E2 reaction. Look, you've got a tertiary alkyl halide here, so you're not going to get a substitution reaction, are you? Okay, you're going to get an elimination reaction. You've got a beautiful ethoxide, which is an unhindered base. We've got, this is our alpha carbon. We've got a beta carbon here, and we've got a beta carbon here. So we've got two types of beta carbons. And if you're like, Mr. Dion, that's a beta carbon too. Yeah, but that beta carbon that I have highlighted in yellow doesn't have any hydrogens attached to it. So that's not very useful, is it? Well, if I draw on the beta carbon that I have highlighted in green, if I draw a proton on that, I'm not very good at drawing betas and hydrogens at the same time. There we go, like that. And if I do the same exercise for the other one, so if I draw a hydrogen coming off here, I'll draw it in blue and draw the beta. Can anybody tell me which one of these protons would be pulled off in preferentially be pulled off? Would it be the blue one or the green one? If I'm using sodium ethoxide. Cha. Thanks, Kayla. Thanks, Josh. You're both 100% correct. Right? It's going to pull off the green one. Why? Because it's going to produce a more substituted alkene, right? I'm going to end up with this as my product. So I'm going to have these two methyl groups over here. I still have this one, but I'm going to have this here. This is going to be my major product. So I'll write it in the green letters, okay? And then for my minor product, since this is my beta carbon here, I'm going to form the double bond here. Now, I'm not going to draw the mechanism for the beta elimination of the blue proton. You can try that yourself, but I'll draw the product, and it's still going to have these two methyl groups, and I'm going to have the double bond here, and this will be the minor product. Let's try, let's do the next one. So we have sodium hydroxide. Sodium hydroxide is an unhindered base. Again, we have a tertiary alkyl halide, so we're not going to get substitution. We're going to get elimination. If I draw this proton in blue, and if I draw this proton in green, again, the reason I'm not doing this one is because that one is identical to the one in blue. Could anybody tell me which one of these would be pulled off preferentially? Would it be the green or the blue? Same rationale as the last one. Yeah, thanks, Josh. Absolutely. 100%. 100%. Love it when my students are right. Okay, this is going to be our major product. Okay, and then our minor product is going to be this. There we go. That will be our minor product. Let's go over the next one quickly. Potassium t-butoxide is a hindered base. Ooh, hindered. Okay, so now we're going to form the exact same products that we did in the previous reaction, aren't we? Right, so copy. I'm just going to paste them here. But now we're going to switch, aren't we? Right, because the potassium t-butoxide is so hindered that it's going to pull off this proton preferentially, right? If you draw potassium t-butoxide, you can just draw it like this, right? We go back here, right? This you can just draw it as this. It's the same thing, okay? You have 1, 2, 3 methyl groups. 1, 2, 3 methyl groups. It's just a really quick way to draw it. Just draw a plus sign with an oxygen with a negative charge on it. Anyhow, right, you can see that that's going to pull off this oops, that's not the right curve there, was it? It's going to pull off this proton like this, loss of leaving group. And so now this is going to be major, right? And then this will be our minor product. Look at this, my friends. You can play God with a molecule, right? Just by choosing the reagent, you can choose whether you're going to get the Hoffman product or the Zaitsev product as the major product. Is that not a good feeling or what? Hopefully you get a good feeling by that. It's just like, yes, I can do what I want with these molecules. I can make them do what I want, which is a good thing. You know, and if you're thinking, oh, Bishop Dion, you're being silly or something. Well, if you think about the advances that have happened in medicine in the past, let's say 70 years, you know, there's nobody who probably would want to go back to living with the medical knowledge that we had or the drugs that we had 70 years ago. Well, you can thank organic chemistry for that, okay? All right. Anyhow, let's move on from there and talk about stereoselectivity. I'll give you a heads up. I know we've only got 2 hours left in lecture, but this is kind of a tricky section, okay? I'll put a little star by it, the stereoselectivity and the stereospecificity of elimination reactions. These are really important. The ACS exam people love to ask questions about section 7.8, and the people who write the MCAT exams also love to ask questions about stereospecificity and stereoselectivity. So let me explain what they are. If you like, what are these two long words, stereoselectivity and stereospecificity? Well, let me go into all the detail. Let's say you have 3-bromopentane, this compound right here. You can see it's got 2 beta carbons. They're identical because there's a plane of symmetry down the molecule. But if you just let's draw these 2 beta protons in here. Well, when my sodium ethoxide, right, when my ethoxide pulls off one of those protons, it doesn't matter. It could pull off this one or it could pull off this one. It doesn't matter, okay? To form our double bond. It doesn't matter. It's going to be indiscriminate to those 2 protons. And because of that, we actually end up with a mixture of cis and trans in this case, or E and Z, whatever you want to call them. And the trans is going to be the major just because of steric hindrance, right? It's not as sterically hindered as this one here. And here's a reaction coordinate diagram where you see that the formation of the cis is higher in energy. And again, it's just because of the steric hindrance. Okay, well, that's, you know, my students are probably like, yeah, I get it. You'd form the trans in greater amount just because of steric hindrance. Students usually don't struggle with that. So here's where it gets really interesting. Notice the title of the slide changed. Look, here it says stereoselective. Okay, what does selective mean? It means, let's say you go to the grocery store and they have apples and oranges, and you like both apples and oranges, but you're selective for one over another. That means you're going to select, let's say you like oranges more. You're like, I'm going to buy both, but I'm going to grab more oranges because I like those even more. That means you're selective. It didn't mean you were discriminate. It didn't mean you discriminated against the apples and didn't get them. Right? You get some of those too, but just not as many. If you're stereospecific, okay, that means you're like, I only like one thing. I'm only going to make one product in this case. So what if you have an alkyl halide like this? And if you're like, oh, jeepers, there's all kinds of labels on that. Well, let me show you what the difference is between this alkyl halide and this alkyl halide. This alkyl halide has 2 beta protons, right? This is the beta carbon. This is the alpha carbon. It's got 2 beta protons. This alkyl halide in this green circle only has 1 beta proton. If you look at this beta carbon here, it's got no hydrogens attached to it. And this beta proton only has 1. And so when you do an elimination on this, since this is a tertiary alkyl, this is a secondary alkyl halide, but it's going to do an elimination reaction, you only get 1 product. You don't get both products in this case. Okay, so it's stereospecifically making just this one. Now, if you're like, why the hell would I only make that one? Well, I could explain it to you the short way or the long way, but I've taught the class enough to know that I should go into some detail about this. And what it has to do with, and our book doesn't use Newman projections to explain this, but I can explain it to you pretty quickly by drawing a Newman projection. Remember Newman projections? I asked you questions about those on a quiz. If you were to look down this carbon-carbon bond right here, what the heck would you see? You would see something that looks like this. Okay, I'll draw it here because there's not a lot of room on here. You'd see the phenyl going off here. You'd see the methyl over here, and you'd have the hydrogen pointing down like this. What's in the back? Well, in the back, you have a bromine pointing up like this. You'd have a hydrogen over here, right, this hydrogen, and then you'd have this tert-butyl group sticking out over here. And so the reason why you only get this product is because the way this Newman projection is set up. The only time the elimination is going to occur, right, when the sodium ethoxide is going to do the proton transfer, formation of the pi bond, and elimination or loss of the bromide as leaving group, is when all of the bromine, this carbon, and the hydrogen are all in a row. Okay, it's when they're all lined up like that. And the angle between the bromine and the hydrogen has to be around 180 degrees. Okay, now our book goes into a longer diatribe about this. So here, I'm going to kind of go over it a little quicker, but it says, in order to rationalize this, you got to look at the transition state. And the carbon-hydrogen bond that I just showed you and the carbon-bromine bond, they have to be in the same plane as the pi bond that's being formed. In other words, they have to be coplanar. And that's what this is right here. Okay, this thing here where they're all in a row like this, that is called coplanar. Okay, coplanar means they have an angle of about 180 degrees. Okay, and that's the only way they're going to eliminate. Now, if you look at that Newman projection, here's the one I drew a couple slides ago. You see how the bromine and the hydrogen are in the same plane. This is called anti-coplanar because the bromine and the hydrogen are anti one another. This is a staggered conformation. And if you're really astute, and I wouldn't expect you to figure this out without me explaining it to you, but what if you rotated this bond, right? What if you rotated that bond so that you had the hydrogen and the bromine in the same plane, but they're up here? They're still coplanar, right? They're in the same plane, but the problem with that is that it's staggered, and we looked at, or sorry, they're eclipsed, and we discussed why an eclipsed conformation is higher energy than a staggered conformation. Okay, so they're eclipsed, and so this is going to be a much lower energy conformation than this one. And so not only do the bromine and the hydrogen have to be coplanar, they have to be anti-coplanar. Now a little, where is it? Yeah, okay, anyhow. So the staggered rotomers, where the beta hydrogen is anti-coplanar, is lower energy, and therefore that's how it's going to happen. Now, as for drawing which group is on which side, you know, when you draw the alkene, that is usually a skill that it takes my students some time to practice. The way I would do it is like this. You have the carbon in the front, which is this one, and then you have the carbon in the back, which is this one here. You can see that the phenyl and the hydrogen, the phenyl and the hydrogen are on the same side. And then, of course, these guys are going to have to be on the same side. Anyhow, my students develop all kinds of strategies for going from here to here, but it just takes some getting used to. Okay, so this is why you know, the book helped you develop your skills in stereochemistry a couple chapters ago, or was it last chapter, or 2 chapters ago? You know, because you really have to be able to manipulate molecules in your mind in organic chemistry, which is not trivial. Okay, so the whole thing about something being anti-coplanar, you're not going to hear me say the word anti-coplanar again in this class, because in order for something to be coplanar, anti-coplanar, it would have to be exactly 180 degrees, but that's not reality. The reality is the angle's probably going to be smaller. It says here around 175 to 179, so it's close to it. And instead of calling that, so instead of being coplanar, it's what we call periplanar. And so we use the term anti-periplanar, okay, instead of anti-coplanar. And that's just to account for slight deviations. In the book, he even says, David Klein himself says, I'm not going to use the word anti-coplanar again. I just explained to you what it is. But from now on, I use anti-periplanar. The guy that I worked for in graduate school was French. I mean, a French Canadian, and he had a strong accent, and you can still hear him saying it's anti-periplanar. Everything was, you know, we were always talking about E2 eliminations all the time. Anyhow, let's see. Assuming they proceed through an anti-periplanar transition state, predict the products for the following reactions. So I find, again, our book doesn't talk about Newman projections at all. The way he does it, and I respect David Klein a lot. I mean, he's an excellent teacher. He just does it like this. He'll say, son of a gun, what kind of a curved arrow is that? He says, you're going to do the proton transfer, formation of the pi bond, and then loss of leaving group, right? This is the proton transfer. This is the LLG, and this is where the pi bond is going to be formed. Now, the way he does it is like this. He says, okay, you've got the carbon-carbon double bond. Since this R group and this R group are both pointing out towards you, right? He says he'll point them down like this, so R1 and R1. And since these two are pointing back in the page, so they're going to end up like this. This can also be another opportunity for my students to make models. Can be really handy for that, or for solving these problems. Now, that works. It totally works. But again, I've taught the class for a long time. If you're the kind of person that likes to draw a Newman projection, I don't advise against it. That's for damn sure. So let's say you look down this carbon-carbon bond right here, and I'm just going to do it for this one. What do you see? You have this hydrogen pointing down. You have R1 going up like this. You have R2 over here. In the back, you've got the bromine going up, so that's good. They're anti-periplanar, the hydrogen and bromine. You have this R group on the same side, and you have this R2 over here. So that when you form the double bond, right, these two groups will be on the same side, and then these two groups will be on the same side like that. Give me a thumbs up if you follow me. I feel like I've been explaining stuff a lot, but I haven't asked you. Is there anything that needs to be cleared up by my students? I understand that this is not trivial, that this is not a simple, you know, see it once and just you understand it for the rest of your life. It's going to take some practice. Okay, good, thanks. At least I got a couple people that follow me. Again, if you're lost or something, or if you find this difficult, just stop me and I can try to slow down a little bit. I know we have a lot of content to cover, but this is really important. Again, if I have many students in this class who've told me, you know, like I'm interested in going to medical school or at least writing the MCAT. And so for those people, this is important, right? For people who want to be successful in this class in organic chemistry too, this is important. Again, same rationale here. The hydrogen and the bromine are anti-periplanar. Nothing wrong with that. So if we draw our carbon-carbon double bond like this, you can see that this R group and R2 are on the same side. So we have R1, and then we have R2, and then we have this R1 over here, and with this R2 over here like that. Anyhow, again, you could practice drawing the Newman projection. I'm not going to do it right now, but you could give that the old college try as well. There we go. Let's see here. If you've got 2 beta hydrogens, there's 2 different rotomers, and if you're like, what the hell is a rotomer? A rotomer is just a conformer that is based off of the rotation of a sigma bond. So if you were to rotate this, you'd get rotomers. Anyhow, so there are 2 different rotomers where the beta hydrogen is anti-periplanar to the leaving group, and so you can get the 2 stereoisomers in this case. Okay, again, this is stereo selective, but not stereo specific. This example right here is basically exactly what we saw way back here, okay? So there's no stereo center here. There's two beta hydrogens, and so we end up with a stereoselective process. But then once you have a stereo center here, you end up with a stereospecific situation. So you know that you need to know the difference between these words, stereospecific and stereoselective. Okay, they come up all the stinking time in organic chemistry, so it's something that you need to be fully aware of as an organic chemistry student. Okay, put another way, stereospecific, the substrate is stereoisomeric, so oftentimes has a chiral center. You just get one single product, so you go from one thing to one thing. Okay, if you have an isomer of it, you're going to get a different isomer as your product. Anyhow, where the hell am I? And then if it's stereoselective, then it's just going to have a preference for one over the other. Okay, give me a thumbs up if you're halfway there with me on the word, a minimum of halfway there on the difference between these two words. It's one of these things I spend more time on as the years go by, because I realize, teaching the subject, when you teach a subject for a few years, you start to understand what's crucial for students, and what students struggle with a little bit more. Some concepts come so quickly to you guys, it's just like faster than me, and other times it takes a little bit more practice. I just want to try one of these problems for now, and then if we have more time later on, we'll come back to this. We'll come back to this question 7.21. Again, if you go in the solutions manual of our textbook, he goes into a whole diatribe, a whole explanation for the answers to these problems. So let's try 7.21b. Just want to try B to start, okay? Because there's really only enough room to solve that one on here. So since we have a beta carbon here, we have a beta carbon here, and we have an alpha carbon here, there are no beta protons over here, but there is one beta proton attached to this carbon. So this is a chiral compound. This is a chiral center. This is a stereoisomeric. Therefore, this is going to be, could anybody tell me, would this be a stereospecific reaction when I do the elimination here, when I treat it with a strong base, or would it be stereoselective? Specific or selective? And it's not a trick. I hate trick questions. Anyone? Yes. It's stereospecific, exactly. Okay, so in that case, when it's stereospecific, it's not going to be just a simple, push a couple of arrows, write down some answers. This means we're going to have to draw a Newman projection. Now, if you're like, Mr. Dion, I thought you said the textbook doesn't use Newman projections. He doesn't. What he does, what David Klein does, is he'll rotate the sigma bond, and then he'll put the hydrogen and the bromine in the same plane. I don't like doing it that way. I think that drawing a Newman projection is actually simpler. So let me show you what you'd get if you draw the Newman projection going down this carbon-carbon bond with your eyeball looking over here. So let's draw. We'd have something that looks like this. Okay, we've got a phenyl group pointing up like this. We've got a methyl group over here, and we've got the beta hydrogen here. That's the hydrogen of interest, right? What do we have in the back? We've got a tert-butyl group pointing down. We've got the bromine pointing off over here. And there's also a hydrogen, which isn't shown, but the hydrogen is coming out like this, so that hydrogen is there. So remember, this is the beta hydrogen. Well, you can clearly see that the beta hydrogen and the bromine are not anti-periplanar, right? We could say not anti-periplanar, okay? So what we're going to do, or what I'm going to do, is I'm going to rotate this bond to put the hydrogen over here, which is going to move the methyl up here, which is going to put the phenyl down here, and that way the bromine and the hydrogen will be anti-periplanar. So I'm going to rotate it. I'm going to rotate the hydrogen 120 degrees. So let's do that. And when we do that, you would end up with this. Son of a gun. Can you draw a better circle than that? Go home. All right, there we go. So now we'd have the hydrogen over here, right? We'd have the methyl group up here. We'd have the phenyl group down here. All the rest is going to remain unchanged. And this bromine, hydrogen, and our tert-butyl group. Look at this, you guys. Now we have the bromine, the 2 carbons, and the hydrogen anti-periplanar. So this is anti-periplanar. There we go. Now we can do our elimination, right? Now the ethoxide is set to come in, and you could practice drawing the mechanism if you want. I'm not going to do it right now. Son of a gun, what did I do? There we go. So I wanted to select this and move it up here. And now we're going to draw the product of the elimination. Oops. So the product of the elimination is going to have a double bond. Okay. Could draw it like this, let's say. Okay, you're going to have the methyl group up here. You're going to have the phenyl group down here. And what's going to be on the same side as the methyl group? What's going to be on this side? Would it be the hydrogen or the tert-butyl group? And it's not a trick. Can anybody tell? Yeah, it's the hydrogen. Absolutely. All right, so that means that the tert-butyl group must be down there. Now, the reason I chose to do this one, I think this is such a wonderful, wonderful example, is because this is a Z alkene, right? This is a Z, right? This is the highest priority, and this is the highest priority. A phenyl is big. Look, we could even draw the phenyl in. Look, a phenyl is just an aromatic ring when it's a substituent. Look at that. Son of a gun, Mr. Dion. What are you doing? There we go. There's some serious steric hindrance there, isn't there? Oh yeah. But remember, the reason this product is formed, is stereospecific, is because the bromine and the hydrogen have to be anti-periplanar to one another. Otherwise, it's just not going to work. Okay? All right. So again, the guided solutions for A and C and some other problems that I've chosen are in the textbook. Again, if we have time on Wednesday, I'll be more than happy to take a look at some more of these problems. If you're trying these problems at home over the weekend, you're like spring break, time to study OChem. If you're studying and there's a problem you run into, say, I can't figure this one out, ask me. I'll either, answer your email, or I will go over it in class with everybody, okay? All right, there we go. One more part of section 7.8. I'm going to cover this part a little quickly. I'm going to speed up a little bit because it's the same rationale as to what we just looked at. However, where the heck am I in my slides here? Beep, 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 beep. However, what was I going to say? I don't remember. Anyhow, this is basically looking at the stereospecificity of E2 reactions, but on a cyclohexane ring. Okay, so going back to cyclohexanes. All right, here I am. What if you want to do a dehydrohalogenation? So again, a dehydrohalogenation, I told you, was just the elimination of H, right, and X. So it could be HCl, HBr, HI, okay? Just losing those two atoms. So what if we wanted to dehydrohalogenate a cyclohexane derivative? So let's say you have chlorocyclohexane. That's all that is, nothing fancy. Well, chlorocyclohexane has 2 conformations, doesn't it? I can have the chlorine axial, or I can have it equatorial. Now, I just told you that in order for an E2 elimination reaction to occur, the hydrogen, the beta hydrogen, and the leaving group have to be, what's that word again? Anti-periplanar to one another. Well, hopefully you can see now why beta elimination can occur when the chlorine is axial, because here you'd have this beta proton down, and you'd also have this beta proton down. This is anti-periplanar, right, to this, as is this. You got 2 protons that are anti-periplanar. When it's equatorial, there are no protons that are anti-periplanar to this guy. None, okay? And if you look at the Newman projection, you can see why that is, okay? I think it's easier to just look at it like this. You see that this is pointing down, this is pointing up. They're anti-periplanar. Good. Here, there's nothing that's anti-periplanar to this chlorine. So therefore, the leaving group has to be in the axial position. Okay, cool. cool. Now, if we look at the two molecules here, it says, which of the two molecules will not be able to undergo an E2 elimination and why? You know what? I'm just going to throw this out here to my students. Let's say I call this A and call this B. Now, this is not an easy question without me having explained it, unless you read the book. But could anybody tell me which one of these would not undergo an E2 elimination if you treated it with a strong base? Could anybody tell me which one just, it's not going to happen? Not going to do it? Yeah. I don't know how you guys know it. I'm hoping that you're reading the textbook and figuring this stuff out. Okay, the answer is B. Okay, we can get a beta elimination with A, but we can't get a beta elimination with B. If you draw the chair structure, it will make it clear to you. So let's draw the chair of A. Okay, and Mr. Dion is going to do his best to draw a chair for you. So let's say this chlorine is up and axial, right? Because the chlorine has to be axial. Well, if I look at the two beta carbons, so this is a beta carbon, this is a beta carbon. Yeah. So if I look at the two beta carbons on, if I label this one beta, I'll call this one beta 1, and I'll call this one beta 2, maybe like that. Yeah, since they're different. Well, on the beta 1, the hydrogen is going down. If it's pointing down, it's got to be down and axial, right? Because remember, it goes up and axial, down and axial, up and axial, down and axial. So that means that this hydrogen, this one right here, is going down and axial. So that means that this is antiperiplanar to this. Now on beta, the beta carbon 2, I've got two hydrogens. I've got one that's going up and equatorial, son of a gun, and I've got another one that's going down and axial. Right? So that means that this this hydrogen is also antiperiplanar. So I've got two hydrogens that are antiperiplanar. If I draw B, however, okay, so I'll draw the chair of B, and I'll just start by drawing it with the leaving group axial. So there it is, up and axial. Okay, like that. Well, if this is up and axial, that means that this is down and axial. And that means that this is down and axial. So on the two alpha carbons, I've got a methyl group pointing down here, and I've got a methyl group pointing down here. That means the hydrogen is up and equatorial. Okay? Those are not, this is not antiperiplanar. This is not antiperiplanar to this, and this is not antiperiplanar. So neither of these are antiperiplanar. So we would say yes for this guy and no for this guy. And you don't even have to draw the chair, because you know that you alternate up and axial, down and axial, up and axial, right? Up and equatorial, down and equatorial. You know that they alternate back and forth. Okay, we could do the exact same exercise here. If this chlorine is down and axial, that means that this is up and axial. That means that this beta hydrogen is down and equatorial. So there's not going to be a beta elimination to form that double bond. So that means that you would not form this compound. You don't have to draw it because it's never going to be formed, but you would not form this. Not, where's my red, big red pen? Where's big red? Not going to happen, okay? Whereas here, if this chlorine is up and axial, that means that this hydrogen is down and axial, and this hydrogen is down and axial. So that means I could form a double bond here to give me this product, or I could form a double bond there to give me this product. So I get two products in this case. Okay, now it says here that one of the alkyl halides undergoes elimination much faster than its diastereomer. And there's an example in the book that explains why. Okay, and you can take a look at that. It deals with menthol and neomenthol chloride. I'll let you take the time to take a peek at that. So there we go. That brings me to the end of section 7.8. Yeah, the rest is just practice problems. This is the last slide. I'll just go over it quickly. Many factors to consider in order to correctly predict the products. Is it going to behave? Is the substrate going to react stereospecifically or stereoselectively? And then if it's stereospecific, you have to figure out which isomer is going to be produced. And if it's stereoselective, you want to figure out which one is going to be the major product, which one will be the minor product. And the last point is this, and you hear me say this all the time, but it's not just me. If you were taking the class with Dr. Anderson or Dr. Schaafstal, who also teaches organic chemistry at UCCS, or anybody who teaches organic chemistry is going to tell you the same thing. The only way that we became proficient in the subject was with lots of practice. Obviously, we had an interest in it. I'm very interested in the subject. But even if organic chemistry is not your favorite class, and I hope it is, but even if it isn't, I promise you that if you practice organic chemistry and are tenacious with the subject, you will begin to master these concepts. Okay, you can do it. People have done it before you, and people are going to do it after you. All right. In the interest of time, I'm not going to go over these problems because we only have about 2 minutes left. But I encourage you to take a look at those products because on next Wednesday, I'd like to spend as much time as we can focusing on practice. Now, again, I've posted videos to my YouTube channel, and I posted these a couple semesters ago, wherein I cover sections 7.9 through the remainder of the chapter. So I encourage you to watch those either today or tomorrow or very soon so that you can finish them before coming to class on Wednesday, and that way we can maximize our practice time in class.